and welcome to the next video in the series. As I promised in the previous video, here in this video and also the next one, what we'll do is we'll take a look at a bunch of problems just to get some practice as to how we come up with algebraic equations and how we solve them. The range of questions, we start with some simpler ones and then we'll take up some questions from chemistry. And let's start with the first problem. Problem 1. Since noon, Paula had 2 cups of tea at 24 calories per cup, 3 slices of pizza at 181 calories per slice, and a slice of cake containing 235 calories. She was inactive for 1.5 hours, burning on average 80 calories per hour. Later, she went running and burned 340 calories. Calculate Paula's net intake of energy since noon. We saw this problem at the end of the previous video, and I thought maybe it's a good idea, just as a reminder, to start this video with that same problem. The solution to this problem, an algebraic solution to it, starts by choosing the unknown quantity symbol. And in this case, because the problem says calculate Paula's net intake of energy since noon, we choose the letter E, or the symbol E if you like, for energy. So E stands for Paula's net intake of energy since noon, and we are asked to find the energy in calorie as a unit, using calorie as a unit. So we'll put down calorie over here. Now we argue that Paula's net intake of energy since noon is equal to the sum of all the intakes minus all the losses. Beginning with, in order, 2 cups of tea at 24 calories per cup, and this will give us the first term, which is 24 times 2. So this term represents Paula's intake of energy from the cups of tea. And then to this we add the intake of energy from the slices of pizza, which is 181 calories per slice, multiplied by 3, as she had 3 slices. This is followed by the intake of energy from the cake, which was 235 calories. And then there come 2 losses. The first one, when she was inactive for 1.5 hours, burning on average 80 calories per hour. And so we subtract 80 multiplied by 1.5. And then we subtract 340 calories, which is what she lost when she went running. So here we have an equation. Now this is the model for problem number 1. As I mentioned before, you can see you can break an expression down into terms using additions and subtractions outside brackets, and therefore this will be, let me try this one more time. There we go. This will be term number 1, 24 times 2, and that's followed by term number 2, which is 181 times 3. Now this second term, 181 times 3, this is the intake of energy from the slices of pizza, and let me also put a box around that. This is followed by 235, which is the intake of energy from the cake, and then we'll put a box around that as well. So far we have 3 terms. And don't forget that we can also use subtractions to break an expression up into terms. So 80 times 1.5 is a term, and then we have 340, which is also a term. Okay, so now we have and on the left side, by the way, we also have a term. E on its own is in a term. So on the left side of the equation we have 1 term, and then on the right side we have 1, 2, 3, 4, 5 terms. And so you notice that you can actually read this as E, which is Paula's net intake of energy since noon, based on what we have here, is equal to the intake of energy from the cups of tea, plus the intake of energy from the slices of pizza, plus the intake of energy from the cake, minus energy that she lost when she was inactive, and then we subtract the energy that she lost when she went running. And this view also tells us how to work out an expression. We obviously need to work out each of these boxes, each of the terms, and then we can add and subtract them. So the next line is E equals 48. That corresponds to 24 times 2. And so the intake of energy from the cups of tea add up to 48 calories. We add the intake of energy from pizza, which is 543. And then to this we add the intake of energy from the cake. That one doesn't change, of course. In this term we only have 235, so we'll just copy it. Then we subtract 80 times 1.5, which is 120 calories. And 120 calories is the total energy loss during the time she was inactive. And then finally we subtract the 340, which is the energy that she lost when she went running. Now we can add and subtract all the terms in one step and write the result as E equals 366 calories. A closing statement will follow. Since noon, Paula had a net intake of energy of 366 calories. Okay, so that's problem number 1. Now problem number 2 is also a very easy problem. It says, so for practice, a bit more practice with easy problems, you bought 3 pairs of socks at $4.20 per pair and 2 hats at $7.25 per hat. What amount of money did you spend in total? Now this is not a science problem, this is a money problem, and for money problems, when it comes to amount, we can use the letter A to represent the value of the quantity that we are seeking. So A stands for the total amount of money I spent, and the unit for it is the dollar. Now we begin with A is equal to, so again the argument is that the amount of money that I spent, the total amount of money that I spent from here is equal to the amount of money spent on the socks plus the amount of money spent on the hats. And so term number 1 becomes 420 times 3, $420 per pair, and she bought 3 pairs, or you bought 3 pairs. And then to this we add the amount of money that you spent on the hats, $7.25 for 1 hat, and you bought 2 hats, and therefore it becomes the second term on the right side becomes $7.25 times 2. And again we can break this expression into terms. So on the on the right side we have 420 times 3, that's term number 1, and then this is followed by 725 times 2, which is term number 2. As usual, on the left side we can also break the expression into terms, and in this case there is only there is only one term on the left side, so the total amount of money that I spent is equal to amount of money spent on the socks plus amount of money spent on the pens. Now we work out the terms. So we have A is equal to term number 1 evaluates to 1260. So in total I spent 1260 on the socks, and then we add the total that was spent on the hats, which comes to 1450. We add them to find the grand total that I spent, and that comes to 2710. As usual, a closing statement follows. In total I spent $27.10. Alright, let's move on to problem number 3 now. Okay, problem 3 says on average we can extract 4 calories per gram of carbohydrate, 9 calories per gram of fat, and 4 calories per gram of protein. A cup of yogurt contains 12.8 grams of carbohydrate, 2.7 grams of fat, and 2.6 grams of protein. Calculate the energy content of a cup of yogurt. Now for these problems, we are dealing with what we call macronutrients. Macronutrients are carbohydrates, fat, and protein, and although we have different kinds of carbohydrates, on average we can extract about 4 calories per gram of carbohydrates. For fat, again different kinds of fat, but on average we can extract 9 calories per gram of fat. And for protein, same thing. It comes to about 4 calories per gram of protein. Okay, going back to the problem that we had. Now in this case the problem says calculate the energy content of the cup of yogurt. So the quantity that we seek is, whose value we seek is energy. And we choose the letter capital E to represent its value with. So the solution begins with E. We define what E is. E is the energy content of the cup of yogurt, and we would like to compute this energy using calorie as a unit. So we start with E is equal to, and the argument here is that the energy content of the cup of yogurt is equal to the energy content of the carbohydrates in the cup of yogurt, plus the energy due to the fat content in the cup of yogurt, plus the energy due to the protein content of the cup of yogurt. For the first one, so term number 1 will correspond to the energy contribution from the carbohydrate content of the cup of yogurt. We can extract 4 calories per gram of carbohydrate, and the cup of yogurt contains 12.8 grams of carbohydrates. So we multiply the two to find the total energy contribution due to the carbohydrate content of the cup of yogurt. And then to this we add the contribution from the fat content at 9 calories per gram and a total of 2.7 grams. This will come to 9 times 2.7. And then comes the last term, which computes the contribution due to the protein content of the cup of yogurt at 4 calories per gram of protein and 2.6 grams of protein in the cup of yogurt. This comes to 4 times 2.6. So now we have 3 terms on the right side. As usual, we use additions and subtractions outside brackets to break the expression into terms. Term number 1 is on the right side, is 4 times 12.8. Term number 2 is 9 times 2.7. And term number 3 is 4 times 2.6. Okay, and also on the left side, as usual, we have the one term which is which contains E, and that's the energy content of the cup of yogurt. Now, what we do next is compute each of the terms and then add them up. 4 times 12.8 comes to 51.2. So the carbohydrates had a total contribution to the energy of the content of the cup of yogurt to the amount of 51.2 calories. For fat, the total contribution comes to 24.3, and for protein, it comes to 10.4. The grand total computes to 85.9 calories. And now we have a closing statement. The cup of yogurt contains 85.9 calories of energy. Okay, so that was problem number 3. Now problem number 4 says there are 15 floors in the building. Each floor has 12 apartments. Each apartment has 4 rooms. How many rooms are there in total? And it should be somewhat obvious that in order to find the total number of rooms, we have to multiply the 3 numbers that are given. If we multiply 12 by 4, each floor has 12 apartments and each apartment has 4 rooms. We can find the total number of rooms on one floor. And then we multiply this by 15 to find the total number of rooms in all of the floors. Now the quantity that we are seeking is amount. The quantity whose value we are seeking is amount. And that's because we are counting. We are trying to figure out how many rooms, so we are counting them. And in the sciences, although you can call this amount or number of, you always use the letter n. But in problems that have nothing to do with sciences, you can choose to use either A for amount or N for number of. And in this case, we start with N, and N becomes the total number of rooms in the building. The unit of counting, of course, is 1, because we are only counting a few things. And N becomes equal to 4 times 12 times 15. Now, this is only one term. There are no additions or subtractions, neither outside brackets nor inside brackets even. There are no brackets and there are no additions or subtractions outside brackets, and therefore the whole thing is seen as one term. On the left side as well, we have the one term that contains n. Okay, so we can work out the one term in one step, and the next line that we get is n is equal to 720 rooms. And now we close, we provide the closing statement. In total, there are 720 rooms in the building. We're going to move on to problem number 5. This problem is from chemistry, and let me clear up, there we go. Problem 5 says calculate the mass of a molecule of H2SO4 given that the atomic mass of H is 1.008 AMU per atom. The mass of an atom of S is 32.07 AMU, and the atomic mass of O is 16 AMU per atom. Let's briefly talk about some of the background chemistry that we need in order to be able to solve problem number 5. And this background chemistry, we begin with atoms. An atom is the smallest piece of matter that contains its chemical properties. So matter breaks down into smaller, you can break matter down into smaller and smaller pieces, and at some point you come to the smallest piece that still retains the character of the kind of substance that you have. If you break, we call those atoms. If you can still break atoms up into smaller components, but you'll find that the identity of the atom will be lost. So an atom can be broken down into its components, into particles that make it up. These particles are such particles as electrons, protons, neutrons, and there are others. But the thing is, once you break those up, once you break the particular arrangement that these particles have, then you will not have the kind of substance that you had anymore. More on that in a bit. So examples of atoms are hydrogen, helium, nitrogen, and so on. Now, for each atom, of course, we have a name and a chemical symbol, so we can refer to the atom and also work with it in chemical equations and reactions. As an example of this, hydrogen, we choose capital letter H to represent hydrogen with. Helium, capital H, lowercase e, and nitrogen is capital N. The names, the symbols are usually made up of either one letter or two letters, and if it's one, the first one is capitalized and the second one, and if there are two, the first one is capitalized and the second one is lowercase. So either one letter, which is capitalized, or two letters, the first one is capitalized and the second one is lowercase. Now this convention is important because if you compare something like CO, and let me actually make this right. Okay, so if I have CO, this refers to an atom of cobalt, but if I make the O capitalized, so if I wrote something like this, then we're talking about carbon monoxide, and these are very different kinds of substances. Cobalt is of course cobalt, but CO this is one atom of cobalt, but this is actually a molecule. This CO with a capital O, it's made up of two atoms, one carbon and one oxygen, and these stick together to form a molecule. That, by the way, is what a molecule is, a group of atoms that stick together and form a unit. We call that a molecule. Okay, so as you can see, casing is important. You change lowercase o to capital O, and you totally change the meaning of what it is that we are dealing with. Right, so next we have the atoms themselves are made up of smaller particles, and we call them subatomic particles. There are quite a few different kinds of particles present inside an atom. But the ones that we care about most, the ones that play a significant role in chemistry, are protons, which we use the symbol P plus to represent them with. The plus signifies that a proton has a charge, has a positive charge. There are neutrons, and these ones are neutral, of course, they have no electric charge. And we use lowercase n with a 0 on top, and the 0 indicates that there is no charge on a neutron. And electrons, we use lowercase e with a minus sign, and the minus sign indicates that an electron carries a negative charge. Alright, so the protons and neutrons are packed at the center of the atom, and in a very tiny small volume called the nucleus. To give you an example of that, take a look at this particular atom. Here we have this particular atom has 2 protons and 2 neutrons. And the 4 of these are packed into a very, very tiny volume. And the electrons go around the nucleus. You have to visualize this in 3D. So some electrons may be going one way and the other ones may be going the other way. And another thing to keep in mind is in terms of how far the electrons are compared to where the nucleus is. One analogy is that if the nucleus had the size of a, let's say, golf ball, then the farthest electrons would probably be in a typical atom would be probably as far away from it as the size of a football field. So the whole atom would have the size of a football field, and the nucleus would be a golf ball at the center. So the nucleus is really, really tiny, and all the protons and neutrons are packed inside the nucleus. Now, what's important about all of this is that the type of the atom, what kind of atom you're dealing with, is set by the number of protons in the nucleus of the atom. So, as an example, hydrogen has only one proton in its nucleus, and you can see we have H1. This is the kind of notation we use when we write chemical formulas by hand. The atomic number, which is the number of protons in the nucleus of the atom, is written as a subscript on the left side of the notation for the atom itself. So we write H1, and that says that hydrogen has one proton. He, and then a 2 here indicates that a helium atom has 2 protons. So actually what we have here in this picture is a helium atom. And the nitrogen atom has 7 protons. Now, if you change 7 to 8, then you no longer have nitrogen. You have oxygen now. So we can actually change one atom into another atom, provided we can add more protons to the nucleus or remove protons from the nucleus. This is, of course, not easy to do. Right. Next, we have number of neutrons. Now, the number of neutrons can vary. You don't have to have a certain number of neutrons inside a certain kind of an atom. So, for example, if you have, let's say, nitrogen, which has 7 protons, you may come across a nitrogen atom that has 7 neutrons. Another one may have 8 neutrons. Yet another one may have 9 neutrons. Now, in theory, you can talk about any number of neutrons. You can talk about no neutrons, and then 1 neutron, 2 neutrons, and then all the way to 1,000 neutrons, 10 million neutrons. But in practice, you don't see all of them. In practice, only a few are stable in nature, and the other ones, owing to all the interactions inside the nucleus, if you have too few neutrons or too many neutrons, the nucleus becomes sort of unstable, and it will not stay what it is. It will break up, and the atom will change into other things. All right, we refer to the atoms of the same kind with a different number of neutrons as isotopes. And as far as electrons go, inside an atom, by definition, by agreement, when we call something an atom, then it means that the number of electrons in it are equal to the number of protons in it. And so you can see, for example, in this atom, I have 2 protons. And that means that because I call it an atom, it has to have the same number of electrons. So it has 2 electrons as well. Now, if you have fewer or more electrons compared to the number of protons, then we refer to the resulting entity as an ion, not an atom anymore. Of course, atoms have mass. And the mass of an atom, there is a unit that's a very small unit of mass called the atomic mass unit, and the symbol for it is AMU, similar to gram and G. So atomic mass unit is a unit of mass, measuring mass, but it's a suitable one for measuring the masses of small things like protons, atoms, molecules. And the reason for that is because again, it's such a small, tiny unit of mass. Of course, it would not be appropriate for us to use grams to measure the mass of an atom with, because gram is a very large unit of mass. And that would mean that we will have a very, very small numerical value going with it. You can think of atomic mass unit and gram as being similar to something like a millimeter and kilometer. Millimeter is useful to measure the values of length, which are small, and kilometer is used to measure lengths that are pretty long, very, yeah. The same thing for mass. We have atomic mass unit, and then we have grams. Atomic mass unit is small enough for us to measure the values of small entities, like which are light, such as, again, protons, electrons, neutrons, atoms, molecules. And we also have grams, which is used to measure the masses of, if you like, chunks of matter that we work with on a daily basis. Now, 1 AMU is the mass of 1 proton. And so, it's also very close to the mass of 1 neutron. A neutron is made up of a proton and an electron, or at least that's a simple picture of it. And so the mass of a neutron is the same as the mass of a proton plus the mass of an electron, except the mass of an electron is so small that usually we ignore that. About roughly 2,000 electrons have the same mass as 1 proton. And so the mass of a proton, again, is 1 AMU, and the mass of a neutron is approximately 1 AMU. And you can see that if we ignore the masses of electrons here and just focus on the masses of the protons and the neutrons, then the mass of this particular helium atom is 4 AMU. All right, so the atomic mass unit is a suitable unit for measuring the masses of atoms and molecules being a group of atoms that stick together. Again, because it's a very tiny unit of mass. Examples of masses of the atoms that we talked about here, the hydrogen, helium, and nitrogen. For hydrogen, it's 1.008 AMU, so just a bit more than the mass of a proton. For a helium, we have 4.003 AMU. For nitrogen, we have 14.01 AMU, and so on. Okay, molecules. A molecule forms when a number of, they can be similar or different atoms, stick together to form a unit. And an example of a molecule is N2O3. And this notation says that there are 2 atoms of nitrogen and 3 atoms of oxygen in the molecule. If there is only one of a certain kind of an atom, then we don't write the 1 down. As an example, we write H2O in place of H2O1. So this molecule of H2O has 2 hydrogen atoms in it, and it has 1 oxygen atom in it. Another notation that sometimes you see is one that uses brackets, like here. It says NH4, and then in brackets we have a 3. Outside brackets, the NH4 is inside brackets, then we have a 3 here, followed by more stuff like PO4. And the intention here is that there are 3 groups of NH4 in the molecule. So each group has 1 nitrogen, 4 hydrogens. And there are 3 groups of NH4. There is 1 atom of P, and there are 4 atoms of oxygen. And of course, the mass of a molecule is equal to the sum of the masses of the atoms in it. Okay, so let's go back to problem number 5. Calculate the mass of a molecule of H2SO4. Now that of course means that there are 2 hydrogens, 1 sulfur atom, and 4 oxygens in a molecule of H2SO4. And here you have it. Let's take a look at this. So there are 2 hydrogens. There is no subscript for S, and that means that there is a 1, and that means there is 1 sulfur atom, and then there are 4 oxygen atoms in that molecule. All right. So we argue that the mass of a molecule of H2SO4 is equal to the mass of 2 H atoms plus the mass of 1 S atom and the mass of 4 O atoms. And then we start the solution, M. We are looking for mass. M is the mass of a molecule of H2SO4, and we use the unit AMU, atomic mass unit, to measure its value with. M becomes equal to the mass of 2 hydrogens plus the mass of the 1 sulfur atom plus the mass of the 4 oxygens. we work out each term. Now this time I'm not going to show you boxes just so you don't get become too dependent on them, but you should be able to tell by just looking at the expression that we have three terms. 1.008 times 2 is 1, 32.07 is the second term, and 16 times 4 is the third term. We work out the terms. So the two atoms of hydrogen have a total mass of 2.016 AMU, plus the mass of the 1s atom, and the 4 O atoms have a mass of 64 AMU. We add all the masses to end up with 98.086 AMU as the mass of a molecule of H2SO4. Closing statement. The mass of a molecule of H2SO4 is 98.086 AMU. Okay, on to the next problem. And this next problem says that we want to calculate the mass of 1 mole, not 1 molecule, but 1 mole of H2SO4. Given that the molar mass of H is 1.008 grams per mole, the mass of 1 mole of S is 32.07 grams, and the molar mass of O is 16 grams per mole. So let's talk briefly about the unit mole. As I said before, we need to have small units and large units to work with amount. Like every other quantity, for mass we have it. We have milligram, even smaller units like microgram, to work with masses which are tiny. And we also have larger units of mass, such as gram, kilogram, megagram, to work with masses which are much larger. And the amount is no exception. We need to have small units for counting a few things and large units to count a huge number of things. And of course, if you're counting a few things, the unit 1 with unit symbol 1, the number 1, can be used to measure the amount. But if you want to measure the value of something, an amount which has a huge number of entities in it, then what we do is we group together a number of ones and refer to the collection as 1 mole. Very similar to putting 12 things together and calling it a dozen. And so the question becomes, well, then how many things should we put together and call 1 mole? Now, to explain how we go about making that decision, let's take a look at a C12 atom. Now, C12, this notation, with the 12 written as a superscript on the left side. The 12 indicates the total number of protons and neutrons in a carbon atom. A carbon atom has 6 protons. And so C12 has 6 protons and 6 neutrons, and the total becomes 12 protons and neutrons. Because each proton has a mass of 1 AMU, and each neutron has approximately a mass of 1 AMU, 12 of them will have a mass of 12 AMU. Now, what we decide to do is to take 12 grams of carbon-12 and call the number of entities in 12 grams of it 1 mole. The reason for picking 12 grams is because it matches 12 AMU. The numerical parts are the same. And so if we call the number of atoms in 12 grams of carbon-12 as 1 mole, then we can say that the mass of 1 carbon atom is 12 AMU, and we can say the mass of 1 mole of carbon atoms is 12 grams. Again, this will be useful because whether we are working later on, you'll see that when we do calculations, whether we are dealing with individual carbon atoms or chunks of it, moles of it, the numerical values in the calculations will be identical. All right, so how many atoms, how many C atoms are there in 12 grams of it? It turns out to be this many, and this is a rounded value, by the way. So this is where that number comes from. There is a reason why we have these particular digits, 6, 0, 2, and so on, and the reason that we have 7 groups of zeros, not 8 of them or 6 of them, which would still be large enough for us to work with. But it turns out that if I want to keep the numerical value of mass the same for 1 mole as it is for 1 atom, then I will have to put together this many molecules of C12 atoms. Now the argument I gave used C12 as an example, but you can use any isotope of any atom. You can even use protons, you can use molecules, and in the end it will come to the same number. Okay, now let's go back to the problem that we had. Now one thing to keep in mind, of course, is that if you break up 1 mole of H2SO4, if you break up 1 molecule of H2SO4 into atoms, you'll end up with 2 hydrogen atoms, 1 sulfur atom, and 4 oxygen atoms. And if you break one mole, so keep in mind that for every 1 molecule, you get twice as many hydrogens, you get the same number of sulfur atoms, and 4 times as many oxygens. And it's true for 1 mole as well. So if you think about, let's say, instead of mole, if you think of dozen, if you have 1 dozen H2SO4 molecules, then if you break them up, you'll end up with 2 dozens of H atoms, because every molecule generates twice as many H atoms. So 1 dozen will generate 2 dozens of H atoms. You will get 1 dozen S atoms, and you get 4 dozens of O atoms. And for mole, it's similar. If you break up 1 mole of H2SO4, you will end up with twice as many H atoms, which means that you will have 2 moles of H atoms. You will have 1 mole of S atoms and 4 moles of O atoms. Now, because the mass of 1 mole of H is given as 1.008 grams, and we end up with 2 moles of H, the total mass of H atoms will be 1.008 times 2. And so we begin our solution with M being the mass of 1 mole of H2SO4 in grams, and M is equal to the mass of 1 mole, which is 1.008 grams, times the number of hydrogen atoms. There are times the number of moles, if you like, of hydrogen atoms, and we have 2 moles of H atoms. And then we add the mass of the S atoms, which is 32.07 grams for 1 mole. And then for 1 mole of oxygen, the mass is 16 grams, and we end up with 4 moles of oxygen. So we multiply 16 by 4. There are 3 terms on the right side. We work them out and add them up. And so the mass of 1 mole of H2SO4 is 98.086 grams. Now let me take a look at problem number 5. Take a look at this one. It says M is the mass of a molecule of H2SO4 in AMU, and you notice that it's identical in terms of the numbers that go into it. These numbers are identical to what we had for the mass of 1 mole of H2SO4. The difference is at the end, the mass of a molecule will end up using the unit AMU, and the mass of 1 mole would end up using grams, but the numerical values will be identical. Okay, let's now take a look at problem 7. Calculate the mass of 15 molecules of NO2. The atomic masses of N and O are 14 AMU per atom and 14.01 AMU per atom and 12.01 AMU per atom respectively. And what we'll do, the kind of argument that we will go through is, if I want to find the mass of 15 molecules, what I'll do is I'll find the mass of 1 molecule, and then I will multiply it by 15. And so we put down M, which is the mass of the NO2 molecules in AMU, and M becomes equal to, so we put the mass of 1 molecule of NO2 in brackets, and then we multiply by 15. And therefore we put down 15, open bracket, and inside brackets we put down the mass of 1 molecule. The mass of 1 molecule is made up of the mass of 1 N atom plus the mass of 2 oxygen atoms. And now we close brackets. So this explains where brackets come from in algebra. Usually, almost always, brackets signify that there is one group, one box, one thing that you're looking at, the property of one thing, and then you multiply by the number of those things, such as the mass of 1 molecule, and then you multiply by the number of molecules. The whole thing on the right side is one term. keep in mind that you find your terms by breaking an expression up along the lines of additions and subtractions outside brackets. Initially, you don't even look inside brackets, and so you see this whole thing as one term. You can sort of imagine that what you're looking at initially when you look at an expression, what you're looking at is a whole bunch of brackets, sorry about that, not a whole bunch of brackets, but empty brackets, if you like. So this is what you look at initially. This is how you see it. It's 15 multiplied by something. Now later, of course, we will at some point go inside brackets, and when we do that, then we talk about the fact that there are two terms inside brackets. But right now, looking at the whole thing from outside, we don't see what's inside brackets, and we see the whole thing as one term. Again, there are no additions or subtractions outside brackets for us to break the whole expression up into terms. Now, within a term, the things that you multiply are called factors. So if I write down, let's say 4 times 3 times 2, and then to this I add, let's say 5 times 8, and let me put a bit of space here. Okay, there we go. So if I put this down, then there are of course two terms in this expression. The terms are 4 times 3 times 2. No, that's not what I wanted. My apologies. Let me try this one more time. Okay. All right. Okay, so yes, what I was saying was that if we have something like 4 times 3 times 2, seems like, okay, I know what the problem is. My apologies, I'll try one more time. 4 times 3 and then times 2. Yes, that should work. Okay, and then we add to this 5 times 8. So my apologies, I'm trying to get used to this kind of interface that I have, and sometimes it can be a bit tricky. Okay, the terms are 4 times 3 times 2, that's term number 1, and then the second term is 5 times 8. Inside the first term, we have 3 factors, 4, 3, and 2. These are things that you multiply. Inside the second term, we have 2 factors. These are 5 and 8. Now you notice that initially you break an expression up along the lines of additions and subtractions outside brackets, and the reason for that is, of course, it's an agreement. This is not an inherent property of algebra. We as humans decided that this is how we're going to decode an algebraic statement, by breaking it up along the lines of additions and subtractions. And the reason for that is because additions and subtractions correspond to the simplest kinds of problems that we solve. Now, beyond additions and subtractions, the next most complex kind of a problem that we solve uses multiplication. And this is why within terms, the next operation that gets priority is multiplication. We'll talk about division later on. And so inside terms, you break an expression up along the lines of multiplication. And just as we refer to the entities that you generate when you break an expression into terms, we refer to them as terms. We also have a name for entities that you multiply within a term, and we call them factors. Term number 1 has 3 factors, term number 2 has 2 factors. With respect to the case when you have brackets, what you do is initially, again, you don't look at what's inside brackets. So initially, if I have something like 3 and then I'm going to multiply this by, let's say, bracket open 2 plus 5, let's say that's what I have. Initially, you view this as 3 times a 3 times brackets. So this is how you view this. This is how you view the problem initially. So it's 3 times something. The whole thing is one term, and we view this as having 2 factors. One is 3. The second one is the brackets. Now, whatever the brackets will come to, eventually you will work them out and you get one number. Let's say you get 14, and then it becomes 3 times 14. So again, if I right now try to say, let's say in this case we would get 7, of course, and if we do work out the 2 plus 5 over here and we put down 7, then our expression becomes 3 times 7, and you can see that we have 2 factors, 3 and 7. That's the way you view this one as well. It's 3 multiplied by the brackets, and therefore there are 2 factors in this expression. All right. Okay, so let me now get rid of all of what we wrote here, all of the additional stuff that I typed. I'm gonna get rid of all of it, and we continue with our solution. And therefore what we have here then is an expression that has 1 term. The whole thing is 1 term. I'm going to put the boxes around it one more time. So 15 times everything that you see inside brackets, that becomes 1 term. And this 1 term has got 2 factors. One is 15, the other one is the bracket. And we need to multiply them. Of course, 15 is just 15, and so we write it down. And as far as the second expression goes, I gotta move this back up. All right, so we write 15 down. As far as the second factor goes, we need to work it out. Now is the time for us to go inside brackets and take a look at what we have. And when we do that, we'll notice that we have 2 terms, 14.01 and 16 times 2. And as usual, we have to work out the terms, and then we can add them up. So the next thing we write is 14.01 plus the second term works out to 32. We continue working out the second factor. The first factor has to wait until the second one is done, and then we can multiply the 2 of them. And now we have 15 times 46.01. So you can see that 46.01 then is the mass of 1 molecule of NO2. That was the N, and this is the O2. And 46.01 becomes the mass of 1 molecule of NO2. Now we multiply this by 15, and we end up with 690.15 AM. And the closing statement follows. The NO2 molecules have a mass of 690.15 AM. Our last problem involves a molecule that whose notation uses brackets. We want to calculate the mass of 4.8 moles of Na4PO43, and the molar masses of Na, P, and O are 22.99 grams per mole, 30.97 grams per mole, and 16 grams per mole respectively. So again, we find the mass of 1 molecule. This is actually an ionic substance, but for now it's a compound. We find the mass of 1 of these, and then we place the whole thing inside brackets and multiply it by 4.8. And so starting with M as the mass of 4.8 moles of the Na4PO43 molecules. I guess the 4 is missing for Na. Let me just quickly add it on. Add the 4. There we go. So Na4PO43 molecules. And this is measured using grams because we are dealing with moles. And so M becomes equal to 4.8 multiplied by brackets that have the mass of 1 Na4PO43. And because we are going to end up with brackets within brackets, I'm going to use square brackets for the outside ones and round brackets for the inside ones. And so we get the mass of these are the 4 Na atoms that's the Na4 part. 1 Na has a mass of 22.99, 1 mole of it has a mass of 22.99 grams, and we have 4 moles of it. And then to this we add the mass of 3 groups of PO4. So that's 3 groups of PO4. And that becomes the full expression. That shows how we end up with brackets within brackets. If you take a look again inside the big brackets, the square ones, then we have 22.99 times 4. That's the mass of Na4. And then plus 3 groups of, each group has a mass of 30.97 due to the P, and 16 times 4 due to the O4. We place the whole thing inside square brackets and multiply by 4.8. Okay, so for one thing, if you have brackets within brackets, it's a good idea to use round brackets for the inside ones, and then switch to square brackets for the outside ones. If you need to have more nested brackets, then you switch back to round ones, and then again square ones, and then round ones, and then square ones. Also the sizes, now with my software I couldn't do this easily, but the sizes of the outer brackets should be bigger. The advantage of switching the type of bracket that you use and also the size of it is that visually it tells us where one bracket, when you take a look at a bracket that begins like this one, you can very quickly visually tell where it closes. It's over here. Both the size and also shape are important in making that kind of connection. And this bracket closes here. Now, if I don't follow these conventions, then what will happen is that it gets a bit annoying to try to decode the expression. So let me show you what I mean. Suppose I didn't use different shapes like square brackets and round brackets, and suppose that I used the same size brackets. My expression would become 4.8 multiplied by 22.99 and then times 4 plus 3 open bracket 30.97 plus 16 times 4 close bracket, and you can see this is not so easy to read as it's not as easy to read as this one, right? Again, I can take a look at this and see quickly that it closes here. When I take a look at this bracket and I want to see where it opens, I have to really look. It's here because this one closes here. So this second one should open there. But here, I can just say this opens here. This one closes there. It's much easier, much more convenient. Remember, readability is important. Okay, so where are we now? M becomes equal to, now we have one term. The whole thing is one term. There are no additions or subtractions outside brackets, and it has two factors. 4.8 is one, and the square brackets are the other factor. We need to work out the factors, and then we can multiply them. The first factor is just 4.8. There is nothing more I can do with it. The second factor, which is brackets, now is the time to look inside and say we have two terms, 22.99 times 4, and then the plus breaks it up. The next term is 3 times the bracket. And therefore we work out term number 1, 22.99 times 4, that gives me 91.96. And then we add to this, now the second term is 3 times the bracket. And again, we have to work out the bracket before we can multiply 3 by it. So we write the 3, and inside the second bracket, inside the small brackets, we have two terms. There is 30.97, which is the mass of one p atom, and then to this we add the mass of the 4 oxygen atoms, which is 64. Well, not atoms, 4 moles of it, which is 64 grams. Okay, we close the brackets and we continue, and becomes 4.8. The first factor has to wait for a long time before the second, until the second factor is done. Again, we need to work them out before we can multiply them. And the first term is now inside brackets. We have 91.96, and then we add 3 times 94.97. 94.97 now is the value of what we had here, the 30.97 plus the 64. Second term still needs to be worked out. Second factor still needs to be worked out, the brackets. Inside it we continue to have two terms, 91.96, which is the mass of 4 moles of Na, plus 3 times 94.97, and that's the mass of the 3 groups of PO4. So the total mass of a molecule of Na4PO43 eventually comes to 376.87. This is the mass of 1 mole, and now we multiply by 4.8 moles. And the total is 1808.976 grams. And then we have a closing statement. The mass of 4.8 moles of Na4 again. Somehow that 4 kept dropping. And I do insist that I should add it on. And there we are. The mass of 4.8 moles of Na4PO43 is 1808.976 grams. Okay, so what we did in this video is we talked about the sampling of problems whose solutions require the use of addition, subtraction, and multiplication. What we'll do in the next video is we'll also add division to the game and see how we can work with division and including the notations that we use to represent division with. Thank you so much for watching this video. I am in a bit of a rush, so I'm going to get going. But please, if you have any comments, please add them on, and have a great day, and I'll see you in the next video. And as usual, we'll be gone in 3, 2, 1.